by the time of 1900 there are many paradoxes coming from many sources. So, including Russell's paradox, Biroli-Footy paradox, so many paradoxes are there. So, then there was the doubt whether whatever we are doing are having some inconsistency in between them. Say I am working in natural numbers, does there exist one inconsistent or unsatisfiable statement which we are not aware of, but it is present, it is deducible inside the natural number system. So, this doubt came. So, then in 1900 when Hilbert gave the problems for the whole century to work out, there are 23 problems. So, among those there were 2 concerning to this. So, one was this, whether natural number system is consistent or not, it was pertaining to this question, and the other question was decidability of Diophantine equations. So, these 2 problems were taken up by logicians, they are easier for them to handle, and Gödel solved this problem of consistency or inconsistency in natural number system, and Turing solved the other problem, that first order logic is undecidable. Therefore, Diophantine equations also cannot be solved, but he has not finished it. It took another 35 years to show that there is no algorithm to solve the Diophantine equations. So, this was the story behind it. Then what happened in 1931 when Gödel proved these theorems, it is told that there is a story. It is told that at that time Hilbert was drinking and he just threw the glass and smashed it, being angry, because he has started a big program for proving the consistency of arithmetic, and that was called the Hilbert's program. So, now Hilbert's program is shattered. So, that was the impact, and it was really considered as a pinnacle of achievement. It is an intellectual achievement of 20th century. That is how the results were considered. So, it is difficult really to complete it in 1 or 2 lectures even, but then this will be the last lecture. So, it is a very fitting lecture for that, we must discuss about it. So, the problem is whether to find completeness in the natural number systems and whether to prove consistency in the natural number systems. Like we have so many conjectures along with paradoxes, we have conjectures also. Now also there are some conjectures in natural numbers which are remaining, like your Goldbach's conjecture, right, which tells that every even number can be expressed as sum of 2 primes, okay. Every even number bigger than 2, except 2, all of them can be expressed. So, these are sort of things which really bothers mathematicians. Then Gödel really proved that, well, there will be some conjectures which will remain unproved. So, that was basically the incompleteness theorem, that there will be true sentences in natural number systems which will have no proof inside the natural number system or whatever theory you have described for the natural number system, right. But it is not so exactly, because there is some constant, like natural number system with only operation as addition is a decidable theory. So, anything you conjecture can be proved within that, but once multiplication is there, it is no more decidable. Then there comes the question of this completeness. So, we will see slowly how this progresses. So, I should give a disclaimer in the beginning that the formal proof anyway we will not be able to do within even 5 lectures, it needs some more machinery, but then I will give an outline and it is almost formal. So, every point I will tell you where formality is lacking and how it can be done. Okay. So, Gödel's proof really had 2 ingenious apparatus. One is, he says that within the natural number system you can express something is provable or not. So, that is a big thing. Something is provable, you can say some predicate of natural numbers is true or false, that way you can express it. So, second thing is, he has achieved some fixed points, in the sense that suppose you have one unary predicate, let us say not exactly predicates, formulas having one free variable, right, they can be considered as unary predicates. So, there suppose you consider b of x or say b of y as one of the predicates, then he says that there exists a sentence x in the natural number system. So, that x if and only if b of x is provable. This is what is called diagonalization lemma, which he proves. These two are the main things what he does. So, b of x means he has to really code every sentence as a number, then b of n really, not really b of x. That is what he is going to do. So, we will do slowly how it progresses. So, the first apparatus we will start with, which is called the Gödel numbers. So, what he does here is just coding everything of first order logic or even second order as a natural number. That is what he wants to do, right. So, before this he starts with one assumption, that suppose we have one theory of arithmetic, theory of natural numbers, which is having also multiplication in it, some reasonable theory we assume. We are not formalizing again, like your Peano's axioms or something. Then we have a theory, say n, and we have plus and we have into, you may have 0 and 1 also there. Suppose you take a theory having this minimum these things, then there can be other operations, predicates, functions you can define from these things. So, suppose this theory is consistent. See, the main thing is if it is inconsistent, then everything will follow. So, it is not interesting. Let us start that one, we have one theory of arithmetic which is consistent. So, let us call it T, that is the assumption. From there only everything is starting. Okay. So, what he wants to do is you give any formulas, any statements or any thing in the first order logic or even second order, where for all over the predicates are there, but he only goes for the first order formalization of arithmetic, where you are not using for all p and others, but they can be included in the theory. So, now what he does is encodes them as natural numbers, that is the first thing. So, how to give numbers to the symbols, right? He just gives a scheme. So, the scheme is, there are many schemes now, but we will go to the original whatever he has done by using the prime factorization there. So, what he does, you just list all the symbols, maybe these things we will be using, and there can be some predicates, some function symbols and variables. So, you may assume that predicates are finite in number, but even if you do not assume, there is a way to give the numbers. So, you first take say P0, next F0, P1, F1, P2, F2. If you have variables, then you can pose them in between, say P0, F0, X0 and so on. Make a list of all these things, right. So, P's can be infinite in number, F's can be infinite, X can be infinite in number, okay. Predicates, function symbols and variables. Then what happens, suppose you take the nth symbol here. So, it is a list, now ordered list. Now, define alpha of a symbol equal to n, when sigma comes as nth in this list. So, somewhere numbers have been fixed. Now, the thing is, given any number you can go back to the symbol also, right. Given any number, natural number, you can go back to the symbol. Then what happens, he introduces beta of a string of symbols. So, not only symbols, we need strings, because we want to formulate or form the formulas, okay. So, we need strings. So, he writes it as say 2 to the power sigma n of sigma 1, which is alpha of sigma 1, 3 to the power alpha of sigma 2, p m to the power alpha of sigma m, where 2 to p m these are prime numbers in that order, right. So, p m is the mth prime, fine. So, now you see that property still holds, that if you are given some number here, you can do its prime factorization right, which is unique. Then find out what are the symbols, sigma 1 to sigma m can be found out, right. It is constructive, it is computable. Is it clear? So beta itself is computable and its inverse also is computable. Given a number, factorize it, get the symbols. Okay. Now he goes to give numbers for proofs also. Okay. So any formula would be a string of symbols. Now we will go for a list of formulas. Fine. So suppose you take a proof that will look like x1 up to xn. Fine. So there you give 2 to the power beta of x1 Pn to the power beta of xn, right. So take any proof. Now it is a finite sequence of formulas. Now each formula has a beta, right. So again take the prime to the power betas. This is also computable function, and you can see if you take these numbers, prime factorization, take the prime factorization, get the indices, get the strings, again factorize them, get the symbols. So you can reconstruct, right. So now what he does, he calls all of these, not he, I am calling. So we will just unify all these alpha, beta, gamma as g, right. So g will be a function from all the symbols we are using, union all the strings, so which includes your formulas, and union all the proofs to natural numbers. Okay. Fine. So that is how this function is defined. G is alpha, beta, gamma, all those, whichever is applicable for whichever it is. So other way you could have started with G as alpha, then extend it to beta, then extend it to gamma, that is your G. Now this G has some properties, like G of G is a function from this, that is the first thing. For every symbol, every formula, every proof, it is defined. Then if you have G u v, u is a string, v is a string of whatever it is, proofs or formulas or symbols, that will be equal to G of u times G of v, because prime factorization is used, 2 to the power something and so on, right. So multiplication is there, multiplication is assumed here inside it. So we are not going beyond arithmetic, and it is constructible. And next way is from any number given, if it is G of something, then that thing can be computed, right. So given n equal to G of some entity, this x can be computed. Fine. So now what he asks us to think is that given any such entity, you think of that entity along with that number. So whenever you say something of true of that number, you might intuitively think it is true of that thing, of which this is the Gödel number, right. So next thing what we will do is use these Gödel numbers to define a particular type of predicates. Let us call it say P r m comma n in the natural numbers, in the set of natural numbers. It is really a relation, that relation is being translated to our language as P r of m n. So this is what we will do for this is m is the Gödel number of a proof of a formula whose Gödel number is n. This is a long statement. It says m is the proof of n. Okay. If you can suppress that G, intuitively it says m is the proof of n. Okay. So m is the Gödel number of a proof, n is the Gödel number of a formula, and that proof is the proof of that formula, right. That is what this predicate is. Then what we do, define P of say g of x as there exists x such that P r of x n and x equal to m. So, this says there exists a proof, right, it is over the first variable. So, there exists a proof whose Gödel number is m, right, and that is the proof of a formula whose Gödel number is n, right. So, it simply says that x is provable, right. So, this g x is really equal to n, you could have written as n here instead of g x. So, on one of the variables we have quantified, so the other variable remains, so it should be p of n, right. So, p of n equal to, there rejects this, it says that formula x is provable, there exists a proof of x, that is what it says, right. So, it means formula x is provable. We have defined the Gödel number of a proof, right, each formula 2 to the power Gödel number of that formula, 3 to the power Gödel number of the second formula, right, p m to the power Gödel number of the mth formula, right. So, Gödel number of a proof is defined, therefore, this predicate says it is a proof of x, x is provable, rather it is not exactly telling that, it is telling p of n means a formula x whose Gödel number, whose proof exists and Gödel number of that x is n, that is what it says, intuitively x is provable, right. So, instead of writing just n, we will go on writing g of x, it will tell us what is that x of which we are telling that a proof exists. Okay. Is it clear? This is the first order we have to go around, p of g of x. Okay. So, this p of g of x, well, before that, when you say that it has a proof where? In our system T, right. So, always that is our assumption, it has a proof means proof in our system T. We will also write something like, suppose you write the turnstile symbol, x is provable, right, x has a proof. So, it means it has proof in T. So, that means we will write like this, we write this x for proof in T, we will just make it abbreviation. Is that clear? So, now let us see what are the properties of this P, probability predicate, let us call it probability predicate. So, what are the properties? First is, if x has a proof, then P of g of x also has a proof. Is it clear? Right. Next, you can say, suppose x implies y, P of g of this implies P of g of x implies P of g of y. Okay. Once you have a proof of x implies y and also you have a proof of x, then you have a proof of y, it is like your modus ponens, from there it is coming. Okay. So, third is P of g of x implies P of g of g of x. Okay. So, which means if x is provable, has a proof, then x is provable also has a proof, right. It is easy to see from this existential formula, but intuitively also it is clear. Fine. First one, if x has a proof, then x is provable as a proof, that is what basically intuitively it means that. Okay. So, it comes from formally it will come from this if you just manipulate the symbols. Okay. Now, there is one more thing we need, we are concerned with consistency. Now, we can formulate consistency with this probability predicates, right. For example, at least formulate inconsistency, let us see what happens. So, 0 is equal to 1 is an inconsistent statement, right. So, we will say that inconsistency is written as P of G of 0 equal to 1, inconsistency, right. 0 equal to 1 is provable and this is a proof. We will take this formulation as a formulation of inconsistency. 0 is never equal to 1, right, in natural numbers. So, when we say 0 equal to 1 is provable, it is inconsistency of natural number system, fine, that is the interpretation. So, when you say it is consistent, our assumption is that natural number system is consistent, right. So, we should have this. It is not the case that 0 equal to 1 is provable as a proof, fine. This is the assumption of consistency now. Okay. So, slowly we will go for other properties of this probability predicate and something else, fine. So, here I am digressing a bit to avoid diagonalization, which is a difficult thing to do. I will avoid it in a different way using some paradox. Okay. So, let us see. Now, look at all the formulas in T having a free variable, one free variable exactly, say n. They are all predicates over natural numbers, right, one free variable. Now, that set is countable, right, all the formulas are countable. So, this also is countable, then we can have an enumeration of it. So, let us enumerate, they are say B 1, B 2, B 3 and so on with one argument each and so on. This is your enumeration, fine. Okay. Now, consider these predicates, not P of G of B n of n. This is a predicate having one variable, free variable, is that okay? So, now this is one of these predicates in our list, which one we do not know, fine. So, suppose it is B k. So, we have B k of n for some k, which k I do not know, right, for some k this happens. Agreed. Now, once B k of n equal to this, so here is n is a free variable, right, then you have P implies P as a theorem. So, P if and only if P is also a theorem, okay. Then you can take universal closure, right, for every n B k n if and only if this side is provable, right, because that is equal to that P if and only if P. Now, once it is for every n in particular, I can take universal specification, take n equal to k, right. So, for n equal to k, I have a proof of B k of k if and only if not P of G of B k of k. Fine. Now, let us give some symbol, instead of always writing B k of k, I write A equal to that. Okay. So, I have now the fifth property, which says A if and only if not P of G of A is proven. Now, you have to play with this A, see what happens. Use contraposition. It says P of G of A implies not A is provable. Okay, one part of it. This not of this implies not of this. Is that right? So, which is equivalent to A implies not P of G of A. So, I get P of G of A implies not A, fine. Okay. Then I have P of G of implies P of G of implies is it okay? Look at 2, property 2 of P. Property 2 says P of G of x implies y implies P of G goes there, right. So, that is what I have done. This thing is already provable. So, I take P of G of here. So, P of G of A comes here and comes here. Is that clear? This one is here, fine. Now, I have already P of G of A implies not A. So, I take P of G of, apply my second property and get this. I use property 1. If this is a theorem, then P of G of whole thing is a theorem. Now, use this one P of G of this and this one modus ponens. So, that gives P of G of P of G of A implies P of G of not A. Right. Again use one again says if P of G of A, then P of G of this is 3, right, not 1. Use 3, property 3. Now, these are the same, right. If x, then y, and you have y implies z. Therefore, if x, then z. Is that right? Is it okay? Or there is another way. I want only P of G of A. So, I can say P of G of A implies P of G of P of G of A, again 3. Use both of the thing and hypothetical syllogism, right. So, this gives, okay, you can write that way, that will be easier to see. G of A implies P of G of P of G of A by 3. Apply hypothetical syllogism. So, by that we get P of G of A implies P of G of not A, right. So, call this as the sixth property. We are going slowly, developing one by one, right. Now, let us take another, say A implies not A implies anything, Yes, this is a theorem in PC really, right. A implies not A implies Q, anything you can write. So, we start with 0 equal to 1. Okay. Now, take P of G of that, apply 1. So, by 1 I have P of G of this whole thing. Okay. Now, what happens? Use 2. So, use 2 and modus ponens, that gives and modus ponens gives P of G of A implies P of G of not A implies 0 equal to 1, right. You have to check each step. See, this is in the form P of G of x implies y. So, by 2 and modus ponens I should get P of G of x implies P of G of y. Clear? Is that right? Once more we can use, because this is also in the form x implies y, right. So, if you use once more, then it will come to once again it gives P of G of A implies P of G of not A implies P of G of 0 equal to 1. Okay, just P of G of goes through implication, that is what it says. So, you get this implies P of G of this implies P of G of this. Okay. Let us keep on writing what we have got. And sixth was okay. Then we are here P of G of A implies P of G of not A implies P of G of 0 equal to 1, fine. Now, look at 5 and 6, let us say 6. This is in the form x implies y, this is in the form x implies y implies z. Your axiom 2 says x implies y implies x implies z, right. X implies y implies z implies x implies y implies x implies z. By modus ponens you will get x implies y implies x implies z, and x implies y is here. So, you get x implies z, right. So, using axiom 2, which is distribution of implication, and modus ponens, twice we have this 7, which says P of G of A implies P of G of 0 equal to 1. Is that okay? From this you should get x implies y implies z. So, that gives x implies y implies x implies z. You have x implies y as 6. So, you get x implies z, right. X is P of G of A, z is P of G of 0 equal to 1. This is what you get, fine. So, by contraposition from 7 we get not of P of G of 0 equal to 1 implies not of P of G of A. Okay. But well, there is another shortcut. Instead of contraposition, we can do that. Let us see. Now let us keep this 7. From 7 we will be doing something. Okay. If A is having a proof by 1 P of G of A is having a proof, right. Now by 7 it says P of G of 0 equal to 1. Okay. This contradicts 4. Is that okay? 4 is, it is not provable, but you are telling it is provable because of your extra assumption entails A. A is a theorem, that is why. Therefore, what we conclude? A is not a theorem, not A, right. A is a theorem giving a contradiction, so A is not a theorem. Okay. Now, if not A is a theorem, okay, then from 5 P of G of A is a theorem. Right. Not A implies P of G of A, contraposition of the other side. Not of P of G of A implies A, therefore not A implies P of G of A, one side of that. So that gives P of G of A is a theorem, but we have already seen if P of G of A is a theorem, there will be a contradiction, right, which is a contradiction. Right. So therefore not A is not a theorem. So that is our 9th. I take next line, if not of P of G of 0 equal to 1 is a theorem, suppose we start with not of P of G of 0 equal to 1 as a theorem. Okay. Then look at 7. Contraposition of 7 says by 7 we have contraposition, right, and contraposition we have not of P of G of 0 equal to 1 implies not of P of G of A, right. So if this is a theorem, then not of P of G of A is a theorem. Is that okay? So then by 5 A is a theorem, which again will contradict, right, which contradicts, let us write 8. Okay. So what do we get? It is not a theorem. Okay. So that is our 10th one, which says and the last one, proof is over. What we have proved, let us see. These three are the main things we wanted. Okay. So, first it says there exists a sentence in T, which is our consistent theory of natural numbers, which is not provable, whose negation is also not provable. Right?
But the sentence is well.
We do not know. We have no idea about A, right? A is that sentence here. So, it only says that provided T is consistent, right? Provided T is consistent. So, in other words, we say every consistent reasonable theory of arithmetic is negation incomplete. So, that is the idea of a negation completeness. At least one of them is a theorem. Here none of them is a theorem. So, it is negation incomplete, right. So, that is your first incompleteness theorem of Gödel, which is also written another way. We may write it also this way: there exists a true sentence in T which is not provable. It is like our earlier proof of x to the power y is rational when x and y are irrational, right. See, one of A or not A is true, either A is true or not A is true in the natural numbers, but none of them is provable. So, there exists one true sentence which is not provable. Is that clear? Fine. You can find out also which one is true and so on, but we are not going to deal with any truth here. So, we can say in that level that one of A or not A is true, but neither is provable. So, there exists a true sentence whichever is it, A or not A, which is not provable. Fine. That is basically the idea of negation incompleteness. Then we have the next one, which says that, well, all these things are provided T is consistent. So, the next one is if T is consistent, then it is not the case that this is what your 10th one tells, right. But what does it say? Can you read this? P of g of 0 equal to 1 is consistency. There is a proof of P of g of 0 equal to 1 is consistent. So, there is a proof of 0 equal to 1 is not provable, which is taken as the consistency, right. So, it says if T is consistent, then consistency of T cannot be proved. Is it clear? See, one thing is 0 is not equal to 1, true. So, 0 is not equal to 1 is provable. It is also provable that 0 is not equal to 1 is provable. Fine. Now, let us look at inconsistency. 0 equal to 1 means inconsistency if it is provable, probability of 0 equal to 1. Now, it is not provable, so it expresses consistency, right, but not that much only. It is provable, we can prove that 0 equal to 1 is not provable, right. That is an expression of consistency indirectly. Fine. So, here when you say we can prove that 0 is not equal to 1 is provable, it also expresses consistency. Gödel really proves that only. If you have different interpretation of consistency, it does not prove that, it only proves this much. So, this theorem is interpreted this way, that if T is consistent, then its consistency cannot be proved by the mechanism of T, because all our proof apparatus is from T only, right. It might be provable by other mechanics, we do not know, right, not by this mechanism. That is what it says. Is it clear? So, after this Hermann Weyl said that God exists because mathematics is consistent, and devil exists because we cannot prove it, right. That is what it says, and there we should end. Okay. So, today only we have seen these 3 theorems of Gödel, really 2 theorems. One is negation incompleteness of arithmetic, another is its consistency we are not able to prove inside the system, both the theorems. Now, the first theorem says also something else. Once you take a reasonable theory of arithmetic, it means you have plus, you have multiplication, and then you have the induction axiom, otherwise you cannot do most of the natural number things. So, once you take the induction axiom, it says it is no more in first order, it is a second order theory, because you have to say for every unary predicate this happens, right. So, it also proves that second order logic is incomplete, whatever axiom system you make for it, it will remain incomplete, right. So, that gives some limit to our thought process itself, that is why it became so famous, right. It is something like a limitation of human reasoning, we are not able to go beyond it, it looks nothing, after that we cannot go anywhere. That is the importance of the theorem.